Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like review of object-oriented concepts and principles, the object-oriented paradigm, basic concepts, software development life cycle and model architectures. Let's get started. Slide 1. The object-oriented paradigm and overview. Today, let's start with understanding the object-oriented paradigm, which is a fundamental approach in software engineering. First, object-oriented programming, or OOP, is a way of designing software by representing real-world entities as objects. These objects combine data, attributes, and behavior, methods, in one unit. Objects are always created from classes, and a class defines what data an object holds and what operations it can perform. For example, if we have a car class, we can create multiple cars like car 1, car 2. A key concept is encapsulation, which means hiding the internal details of an object and exposing only what's necessary. This protects data from accidental modification. Inheritance allows us to create new classes from existing ones, so we can reuse code efficiently. For example, a sports car can inherit features of a car and add more. Polymorphism means one interface with many forms, like the same function name performing differently depending on which class is using it. Another concept is abstraction, which means hiding unnecessary details and focusing on essential features. For instance, when you drive a car, you don't need to know how the engine works. Thus, OOP makes programs modular, reusable, secure, and easier to maintain, and that's why it's widely used in modern software development. Slide 2. Basic object-oriented concepts. Let's now break down the basic building blocks of OOP to understand them clearly. First is the class, which is like a template for creating objects. For instance, a student class can define properties like name and roll number. An object is a real instance of a class, like student1 created from student. Encapsulation means bundling data and methods inside a class. This protects data from direct access, making software more secure and organized. Think of a bank account class hiding balance details. Inheritance allows a new class to inherit properties and methods of an existing class, promoting reuse. For example, dog class inherits from animal. Polymorphism lets us use the same method name but with different behaviors, like draw in circle and square. Abstraction lets us hide complex details and show only relevant parts, like a TV remote only showing buttons to users. Message passing is how objects communicate by calling each other's methods, like car, start engine. Dynamic binding means method calls are resolved at runtime, which supports polymorphism. Modularity ensures breaking the system into smaller, manageable parts, which simplifies development. These concepts are essential for designing robust and maintainable software systems. Slide 3. Software Development Life Cycle, SDLC, in OOP. Now, let's discuss how object-oriented software engineering fits into the software development life cycle, SDLC. SDLC is a step-by-step process to develop software efficiently, from idea to final product. First, requirement analysis helps us gather and analyze what users need. Then, in system and software design, we plan the system's structure, defining classes, objects, and their relationships using OOP principles. In implementation or coding, we write actual code based on the class and object designs. Testing is crucial to check whether the software works as expected, through unit tests, integration tests, and system tests. Deployment is when the software is delivered to users and made live. Maintenance involves fixing bugs and adding updates after deployment. OOP makes SDLC smoother by ensuring modularity, reuse, and ease of maintenance. classes and objects identified during design flow seamlessly into implementation. Also, iterative development is easier in OOP, meaning we can improve and refine the system at each stage based on feedback. Slide 4. Advantages and disadvantages of object-oriented paradigm. Let's now look at advantages and disadvantages of the object-oriented paradigm so you can evaluate where and when to use it. Advantages. 1. Modularity. Objects act as independent modules, making large systems easier to manage. 2. Reusability. Classes can be reused across different projects, reducing development time. 3. Scalability. Easily add new features by extending classes without affecting existing code. 4. Maintainability. Encapsulated code is easier to update and debug when changes are required. 5. Flexibility. Polymorphism allows methods to adapt according to object type. 6. Security. Encapsulation hides internal data, protecting it from external modification. 7. Productivity. Using existing components and patterns speeds up development. 8. Clear mapping to real-world. Objects represent real-world entities, making design intuitive. 9. Extensibility. Easy to enhance existing functionality through inheritance and overriding. Disadvantages. 1. Steep learning curve, difficult for beginners to grasp fully. 2. Complex design. Designing class hierarchies can become complicated. 3. Performance overhead. OOP features like abstraction and dynamic dispatch can slow performance. 4. High memory use. Managing objects requires more memory than procedural code. 5. Not ideal for small programs. For simple tasks, OOP may be overkill. 6. Tightly coupled classes. Poor design can cause dependencies that are hard to manage. 7. Extra design effort. Requires time to plan before coding. 8. Not all problems fit OOP. Some issues are naturally better solved procedurally. 9. Object creation overhead. Large number of objects can lead to performance and memory issues. Slide 5. Model architectures in object-oriented software engineering. Let's now understand various architectures used to model object-oriented systems. 1. Object model focuses on identifying objects, their attributes, methods, and relationships. Example: an online store has product, customer, order. 2. Class hierarchy shows inheritance relationships like animal greater than dog greater than bulldog. Helps visualize reuse and extension. 3. Dynamic model represents how objects interact and change over time, shown through sequence and state diagrams. 4. Functional model describes data flow and function transformations, focusing on how data moves and changes. Example: order placement process. 5. Component-based architecture. Systems are built from reusable software components. Example: login component reused in different apps. 6. Client-server model divides system into clients requesting services and servers providing them. Example: web browser and server. 7. Model view controller (MVC) separates data, user interface, and control logic, promoting organized code. Example: web apps with separate UI and backend. 8. Layered architecture breaks software into layers like presentation, logic, and data access for better organization. 9. Repository model uses a central data store accessed by multiple components. Example: a shared database. These architectures help in building large, organized, and scalable systems using OOP principles. Slide 6. Difference between object-oriented and procedural paradigm. Let's end by understanding how object-oriented paradigm differs from procedural paradigm. Focus. OOP focuses on objects and data, while procedural focuses on functions and procedures. Data access. OOP emphasizes data security and encapsulation. Procedural allows global data access. Reusability. OOP supports reusability through inheritance. Procedural needs code duplication. Modularity. OOP organizes code into classes and objects. Procedural uses functions and modules. Extensibility. OOP allows easy extension of existing classes. Procedural is harder to extend. Data security. Encapsulation in OOP protects data. Procedural lacks such mechanisms. Approach. OOP uses bottom-up. Procedural follows top-down approach. Maintenance. OOP is easier to maintain due to modular structure. Procedural gets complicated in large systems. Example. OOP languages include Java, C++. Procedural includes C, Fortran. This gives a clear view of when and why to choose OOP for modern software development.